now. Yay. So this morning, we're lucky to have Takafumi Kaneko speak to us, and it's part of the COFFIES Flux Transport and Emergence theme. So just to introduce him briefly, he spent much of his time being educated at the University of Tokyo. Both his bachelor's and his PhD were conducted there. And after that, he became a University of Tokyo JSPS fellow, and then moved to Nagoya University, where he was a researcher and an assistant professor before joining HAO and Lockheed Martin as a postdoctoral fellow. And I believe your appointment at Lockheed Martin and HAO is only a year long. Is that correct? So it's a very short time.
Yeah.
But this morning, he's going to be talking about the impact of subsurface convective flows on the formation of sunspot, magnetic field, and the energy buildup. So go ahead.
Okay, so I share the screen. Okay, so thank you very much for introduction, and thank you very much for the opportunity to talk about our recent study. So today I will talk about our recent numerical simulation on the flux transport and flux emergence. So as an introduction, of course, you all know about solar flares, but I introduced solar flare. So solar flares are caused by the release of magnetic energy, and the mechanism of magnetic energy release is basically reconnection or image instability or like that. And large flare basically happen in sunspot or decaying active regions. And we empirically know that the large flare, especially X-class flare, cause in the delta sunspot. And delta sunspot is characterized by the bipole in the same penumbra. And this is a bit old paper, but by the statistical study. So basically, all of the X-class flare, especially X2 larger than X2 flare, always occurred in the delta spot. An important parameter of large flare is that free magnetic energy. And the definition of free magnetic energy is the volume integration of the difference between the magnetic field and potential magnetic field. And potential magnetic field is basically current-free magnetic field. So because the potential field does not have the current, there is no Lorentz force and there is no ohmic diffusion. So no magnetic field can be converted to the thermal or kinetic energy. And if deviated from the potential field, it is so the magnetic energy has room to convert it to the thermal or kinetic energy. So it is free magnetic energy. And if we can obtain the 3D magnetic field, like this example is, for example, the data constraint model. And yeah, so if we can have 3D model, we can evaluate the free magnetic energy as a volume integral. So like that. So we can, for example, we can trace the temporal evolution of free magnetic energy. And at least free magnetic energy is necessary to cause large flare. And if there is no free magnetic energy, no large flare can be caused. And so this is a case of that was a case of a 3D magnetic field, but even from the 2D magnetic field, we can somehow know there is storing magnetic energy or not. And the parameter is non-potential field, defined as observe the value of difference of magnetic field compared with the potential field. So this is not the dimension of energy, but the concept is similar to the free magnetic energy in terms of the deviation from the current free magnetic field. And usually the strong non-potential field is found along the polarity inversion line of the delta spot. For example, in this figure, blue and yellow shows the negative and positive vertical magnetic field, and this panel C and G shows a non-potential magnetic field. And basically, non-potential field is distributed along the polarity inversion line. And all active region producing X2 flare had intense non-potential magnetic field according to the previous studies. And of course, we can say that strong non-potential field does exist before the large flare happened, but we can't say that if there is a strong non-potential field, the large flare always occurred. We can't say that. And because the magnetic energy buildup and releasing energy is different process. So that is a difficult aspect of the flare issue. But today I would like to focus on the energy buildup process, and the energy releasing part is out of scope in our study. So what is the mechanism of energy buildup? And this is also studying very long time. And basically the possible process is converging and sharing motion in the photosphere and or flux emergence. And this is confirmed from many observations. And the next question is what drives the converging and sharing motion and or flux emergence? And because we know that the solar interior is filled with convection, so the convection is convection should important role. And also the magnetic Lorentz force that has flux drop has also may deform themselves. So yeah, maybe the convection or magnetic Lorentz force or both must be important to answer the question. And how can we know the relationship between the photospheric processes like converging motion or sharing motion or flux emergence and the internal process like flux transport by convection or magnetic evolution inside the inside the sun? So basically photosphere can be observed in detail, but it is difficult to observe the interior of the sun. So the numerical simulations have been performed for a long time. And this is one example of the flux emergence simulation by Rempel and Chen 2014. And basically by including the realistic convection, we can reproduce the realistic magnetic distribution of the sunspot like this. And we can change the magnetic parameter. For example, panel A shows that the result using the initial field strength as 10.6 kilogauss. And in the case of B, the magnetic field strength is twice larger. And this is kind of the physical difference of the difference of result is due to the physical difference. But one issue of this kind of simulation is the effect of bottom boundary condition. So panel B and panel C and panel D shows the results of result of the same field strength, but the different bottom boundary condition. So, for example, a difference of bottom condition is like, for example, both inflow and downflow are permitted in the bottom boundary, or only inflow is permitted, or only outflow is permitted, or like that. So even it is a difference of bottom boundary condition, it really affects the magnetic distribution on the photosphere. That is because, so in the right panel shows a cross section along the height, and the color is a magnetic field. And basically, as time goes on, the magnetic field reaches to the bottom boundary. So actually, the bottom boundary influences the distribution of the magnetic field at the surface of the sun. So this is one issue of the simulation, this kind of local box simulation. And there is attempt that improve the simulation. So this is example of Chen et al. 2070. And main improvement in their study is that they used the initial flux model from the dynamo simulation. So at first they performed dynamo simulation and obtained the flux emergence. And using the solution of the flux slope reproduced in the dynamo simulation, so it is actually kind of realistic flux model. And they use the realistic flux model as an initial condition and then perform the local box simulation of the flux transport. And using the realistic initial flux model, they successfully reproduced the realistic complicated magnetic distribution in the photosphere. But there are still the issue of the effect of boundary condition. So this, and not only boundary condition, it is also the horizontal boundary condition also influence the result. So they change the depth of the bottom boundary condition, and also they change the width of the simulation box. And actually the results are different. So this kind of issue is somehow problematic. So we have to do something to take care of that. And the simple way is just extend the bottom boundary to the deeper layer. And of course, it is difficult because of course, extending the simulation box means that we need more grids. So it consumes more numerical resources. And also the time scale of photosphere and time scale in deeper layer are completely different. So including the different time scale phenomena in one simulation is basically not good for efficiency of the numerical simulation. So basically it was difficult. But now that the performance of numerical supercomputers are good, so we can somehow extend the bottom boundary condition to deeper. And recently, Hotta-san in Chiba University developed the numerical code to solve the deep layer of the convection zone, including photosphere and chromosphere. And for example, this is a result of Toriumi and Hotta 2019. And this flux transport simulation includes the simple flux model, relatively shallow layer of around 15 megameter. And as time goes on, by the downflow, so basically downflow downflow plume exists to the deeper layer until to the end of the deeper layer, and the flux lobe was pulled to the deeper layer. Then in the photosphere, the end of the flux lobe approaches each other, then finally collided. The opposite polarities are collided. So by this process, the delta sunspot was reproduced in their simulation. So inclusion of the, and of course, not of course. So in this simulation, basically the flux lobe did not reach to the bottom boundary. So basically we had less effect of the bottom boundary in this simulation. So it is kind of a self-consistent magnetic evolution inside in the sun. So later on, their group also performed another simulation, and they also created the beta type magnetic distribution. So simulation code is same, and actually the magnetic parameters are same, but the difference was convection. So this figure shows that the vertical velocity at a certain height, and red is downflow and blue is upflow. And so left panel shows the flow distribution used in the Trim and Hotta 2019, and this simulation reproduces delta spot. And right panel shows the flow distribution of in the Hotta and Ijima 2020, and this resulted in beta spot. And from just looking at that, we can't know what is the essential difference. So basically the flow distribution is just complicated, and we don't know what is the essential thing to determine the magnetic distribution in the photosphere. So we would like to solve this problem by new approach. So yeah, so basically the aim of our study is to reveal the impact of convective flow in the convection zone on the formation and evolution of sunspot magnetic field and their energy buildup. And method is basically we performed a parameter survey, but including many cases. And we performed a statistical study. We applied a simple statistical analysis to the result and extract the essential feature of the which is important to determine the magnetic distribution, especially the formation of delta spot in the photosphere. Okay, so I explained the numerical setting. So at first, we reproduced the solar convection without magnetic field. And basically, we wait until the statistical equilibrium is achieved. And we set the local simulation box with this size. So basically, horizontal size is 100 megameter. It is basically typical size of the supergraduation. And we add the flux tube to a certain depth. And then just let it be. So basically flux transport may transport the flux tube to the upper layer or lower layer or horizontal layer, we don't know, but maybe flux tube is transport. Yeah.
Excuse me, do you have twists? Do you have twist in the flux tube?
Yeah, there is twist.
Yes.
And this flux tube has positive helicity in this case.
Okay.
So, and grid size is basically moderate, not extremely high resolution, but yeah, because we have to do many parameter survey, we use the moderate resolution of the simulation. And this
can I ask if is your flux tube always horizontal or is sometimes it's vertical?
This is always horizontal. So main axis is always horizontal and always same direction. So this is a basic equation and basically MHD equation. And we use the background stratification using a model S. And the energy equation has the radiative heating, and the radiative heating came from solving the radiative transfer. But in our simulation, the radiative transfer is solved only along the Z direction, vertical direction, and like that. And we use the supercomputer Fugaku installed in RIKEN in Japan. This supercomputer was fastest in the world until last year. Now that second rank. But so we were able to use such kind of large chemical resources. So we actually carried out the large number of parameter survey. So this is a typical case of the result. So left panel shows a vertical velocity. Red is downflow and blue is upflow. And right panel shows the magnetic field strength. Color shows magnetic field strength, and the gray scale at the top is a vertical component of the magnetic field. And in this simulation, the flux lobe was deformed by the downflow, and in the photosphere, the positive and negative flux collided each other. Then eventually the delta type magnetic distribution was reproduced. So this is typical case, and we performed the parameter survey, and the basically field strengths and twist are fixed for all cases, and horizontal positions were changed by 31 cases. And actually, for example, in the right panel, the horizontal line shows the axis of the magnetic field. And we changed the position of initial flux tube by 3 megameter uniformly. So there is no bias for the position of the position. So each simulation has one flux tube, but the position of the flux tubes are different. And by changing the position of the flux tube, basically the turbulent flow, convective flows surrounding the flux tube are different. So basically the result should be different. And this only shows the difference of horizontal position, but we also change the depth of the initial position in 3 cases. So in total, we performed 93 RMHD simulations.
Hi.
And
Hi, can I ask a question in the previous slide? Hi.
Yeah.
So you seem to be having a super granular scale structure. The downflow is, so you introduce the flux tube after you form the super granule, or it's from the beginning?
From the beginning, already supergranular scale downflow existed.
Oh, okay.
Yeah, so we wait for the statistical equilibrium and was achieved in the convection zone. And then, so for example, suddenly introduce the flux tube at the certain layer.
Okay. All right. Thank you.
So this is the result of all cases. So this includes 93 panels, and each is a different case. And this grayscale represents the particle component of magnetic field at tau equal 1 layer. And yeah, as you can see, actually there are various kinds of magnetic distribution, and magnetic parameters are same, but just changing the position of the initial flux tube, the resultant magnetic distribution are completely different. And we can see that sometimes so positive and negative patch are collided, and delta type distribution are reproduced. But in some cases, positive and negative patch does not collide, and just beta type spot was reproduced. And also sometimes the flux emergence never happened. So like this panel or like this panel. So this panel actually, sorry. So yeah, so because we don't have any bias for the initial position, so not only flux emergence, but also we reproduce the no emergence case. Yeah. And this is a temporal evolution of magnetic flux of all cases, and also the magnetic flux versus the magnetic emergence rate. So compared with the previous observation, our result is basically the case that magnetic flux is large. So yeah, basically our simulation reproduces the cases of large magnetic flux case. But of course, as I said, there is no flux emergence case. And so sometimes the flux is very small. And also in our simulation, the maybe flux emergence rate is a bit larger than the observation, but we don't know why this happened. But anyway, so this is a comparison with the observation. And so I will discuss the non-potential field. So basically, this is a time evolution of the particle component, and this is a time evolution of non-potential field. And basically, the non-potential field are distributed along the polarity inversion line. This is very consistent with the observation. And so to extract the trend, we averaged the we temporarily averaged the non-potential field, and this panel shows the temporal mean of the non-potential field in each case. And after that, we summed up all of this trend and normalized, then derived this distribution. So in this figure, basically bright region, so it means this value is close to 1. So non-potential field is likely to be created. But in dark region, non-potential field is not likely to be created like this. So this figure represents such kind of trend. And there is a question, I guess.
Yeah, sorry to interrupt. I just had a quick clarification question, if I could. So is it correct that you have for each case the same initial hydrodynamic state, the same initial field strength for your flux tube, and the same helicity for each initial flux tube? Is that correct?
Yeah.
Okay.
Thanks.
Thanks.
So difference is basically the position of the flux.
And its position and depth, right? It's horizontal and
Yeah, depth is, yeah.
okay. Thank you.
So next we want to know why this distribution is created. So we compare this non-potential field trend with the mean velocity field at each height. So basically, the velocity structure at different heights are completely different. So if it is shallow, basically very tiny structure are dominated. But as going to deeper, large scale structure appears. So we computed the correlation between this map and this map, or this map or this map, like that, and compare the correlation coefficient as along the depths. And so basically we compare the vertical velocity and also horizontal divergence and also vertical vorticity. So basically horizontal divergence is just horizontal divergence, and the vertical vorticity is a rotational motion, and the axis is vertical direction. And this is a result. So the horizontal axis is a depth, and the vertical axis shows a correlation coefficient. And black line shows the correlation coefficient of the non-potential field trend versus the distribution of downflow. And red is for the horizontal divergence, and blue is the vorticity, vertical vorticity. And as you can see, so basically the vertical velocity has relatively high correlation with the non-potential field trend. So for example, maximum is 0.7, so it means relatively good correlation. And for the horizontal divergence, the correlation is up to 0.3, so maybe there is weak correlation. And blue is vertical vorticity, and actually apparently there is no correlation with non-potential field distribution. And so we also thought that the tiny structure tiny structure decreases the correlation coefficient. So we try to adapt the low-pass filter. So for example, if this is a low-pass filter of the mode root square 2, and for example, if low-pass filter applied, the small tiny structure were removed, and only the larger structure were extracted. And again, we calculated the correlation coefficient with the non-potential field trend distribution. And this is the result of the correlation between non-potential field versus downflow. And the upper panel shows the correlation coefficient as a function of depth. And the cutoff frequency of low-pass filter is square root 2 of mod square root of 2. And in this case, actually the correlation coefficient increases compared with the original case. So the higher in the area higher than minus 50 millimeter, the correlation coefficient is basically over 0.8, and maximum correlation was 0.9. So it's a very good correlation. And the lower panel shows the correlation coefficient as a function of depth and also the cutoff frequency. So basically, larger correlation can be found upper than minus 50 megameter, and basically larger structure. So there is no correlation with the tiny structure. And yeah, we confirmed that only the larger scale structure correlated with the non-potential field distribution. And next, I show the correlation coefficient with the horizontal divergence. So if you're using the original horizontal divergence, the correlation was just 0.3. But if we adopt the low pass filter, the correlation coefficient was improved to 0.8. And the depth is a bit shallower than the downflow. So basically over minus 30 megameter, the correlation is good. And the lower panel also shows that the correlation coefficient as a function of depth and cutoff frequency. And basically the trend is same as basically trend is the same with the result of the downflow case. Then the interpretation is that, so basically downflow in our model, basically there is a downflow through inside the simulation box from the initial state. And so basically we distributed the flux lobe everywhere in this area, but downflow always follow the converging motion due to the mass conservation. So basically flux gathered, extracted to the downflow area, then emerge and pulled by downflow, and actually the energy is built up along the polarity inversion line. That is an interpretation of our analysis. And we also, this is the result of the case of vertical correlation coefficient versus vertical vorticity. And the low pass filter was applied to the vertical vorticity, but in this case, the correlation coefficient does not exceed 0.5. So again, the vertical vorticity is nothing to do with the non-potential field creation. So yeah, but actually we saw that sunspot rotation in our simulation. So for example, in this case, the sunspot rotate anti-clockwise, apparently. And we investigated what causes this anti-clockwise rotation. And actually, we found that the positive helicity, which has the initial flux of has, is converted to the rise of the magnetic field. So the right panel movie shows a conversion of helicity to rise. And because the fracture has positive helicity, sorry. So if the two ends of the polarity approaches, the helicity is converted to the rise, and the anti-clockwise rotation is driven. So basically, this happens almost all cases in our simulation, which create a delta spot. So we think this is one mechanism to transport the non-potential energy to the photosphere. So this is the last slide. So until now, I computed the correlation coefficient using the temporal evolution of the data. So it means that the convection field were affected by the magnetic field. But in this figure, we also try to compute the correlation coefficient with the initial velocity field. So initial velocity field means that, so basically initial velocity field is not affected by the magnetic field. So yeah, like that. So we computed the correlation coefficient between the non-potential field versus the downflow and horizontal divergence at T0. And the solid line shows the result. And basically, we can find the correlation coefficient of 0.7 over the minus 50 millimeter. So basically, we can find a good correlation between the future magnetic distribution and the initial velocity field. And in our simulation, the flux emerges time is after 20 hours. So we can expect that the high free energy region can be above the downflow plume even before flux emergence. And maybe the leading time is 20 hours, so it means 1 day or like that. So this is a summary. So we performed 93 RMHD simulation on flux transport, and we performed a parameter survey on the initial position of the flux tube. And basically, various kinds of magnetic distribution were created only by the difference of the convective velocity field surrounding the initial flux tubes. And we found that the non-potential magnetic field is likely to be created above the downflow plume. And basically, downflow plume is followed by the converging motion. So the converging motion basically collect the flux to the downflow area. So basically, the location of non-potential field is likely to be above the downflow. And we also found that the sunspot rotation was driven by Lorentz force, and vertical vorticity of the convection is nothing to do with the rotation of the sunspot. And we found a correlation between the distribution trend of non-potential field and the converging flow, downflow and converging flow at T equals 0. So this might be helpful information to find pre-emerging region even before flux emergence. So this is the summary of our work. And I'm not expert of helioseismology, so I also want to ask you that can we detect the downflow plumes or converging motion by helioseismology? And if possible, to which depths? That is my question. So thank you very much.
Thank you. And to your question, who wants to answer from the helioseismologists in the group? Let's see, Junwei, I see your hands raised.
Right, I can answer this question. For now, I think we can confidently derive the downflow structures by use of helioseismology up to 20 megameters in depth. So, but on the other hand, I'm not sure about the temporal scale. For example, in your simulation, you use the stable convective structure that doesn't change with time. But in reality, I think those structures evolve with time. For example, the supergranulation has a lifetime of about 20 to 30 hours.
Mhm.
So I'm not sure if these structures, the change of these convective structures during the time of the emergence, how does this change, how does this affect your simulation of magnetic emergence?
So in our simulation, also the convective flow changed with time. So basically, we derived the mean velocity field and compared with the non-potential field. So actually, because the temporal variation of the convective flow, so correlation coefficient decreases from 0.9 to 0.7, but still we have good correlation, even including the temporal variation. So I think I'm optimistic to use the compare with the observation. So if we have a chance, yeah.
Can you remind us at what depth you introduced the flux in your domain?
Basically 20 megameter to 30 megameter.
Okay. And do you vary that depth?
Sorry.
Do you vary it for your different scenarios?
Actually, the only difference is the amount of flux. So if it is set to the deeper layer, basically amount of flux in the photosphere decrease. But the basically difference was like that.
Okay, thanks. All right, Nick, I see that you raised your hand, and then Paul Rajaguru.
Yeah, thanks. Hey, that was a very interesting talk. Thanks very much. I got a couple of major questions I just want to ask. First of all, you have one supergranule in your box basically, and so you have one of these things happening. If I had a box which was much wider and had 20 supergranules in it, would I get 20 delta spots?
So if we extend the simulation box, basically, yeah, there should be multiple supergranule, but also there is a very large structure. So it does not exist in the sun. So basically, very large structure larger than supergranule will be included if simulation domain is extended. So we thought that it is not realistic in the sun. So we just limit the simulation box. So currently we don't know how to remove such kind of very larger structure than the supergranule. So yeah, just extending the horizontal width is not so good for realistic discussion.
Okay, but if the process for forming your delta spots operates on a supergranular scale, what is it in the sun that means that you don't see these things appearing on supergranular scales?
Sorry. So,
I mean, you're saying that the process that forms delta spots is supergranules, right?
Yeah.
So on the sun, what is it that stops one of these things forming for every single supergranule?
Yeah, but we also have to consider where the flux tube is formed. So yeah, that is another problem, but basically, yeah. Yeah, basically.
I mean, I was going to say, I think the answer, maybe if I interpret this work correctly, is that not every single supergranule has a large flux tube resting at 20 megameters below it.
Okay, but that then means that the stuff that is emerging to that point has to have something which is on supergranular scale. So the wavelength of the magnetic buoyancy instability or whatever has to be supergranular, which is very, very high frequency for an instability like that, right?
Yeah.
Yeah, I think so.
So maybe this leads into my second question is, in your simulation, you have a very nice, fully formed, stable, beautiful, cylindrical flux tube at 20 megameters. What happens if you start it much lower down?
So basically, if we set more deeper, no flux appeared in the photosphere.
Okay.
Because it decayed during the flux. So
the too diffusive?
Yeah, it's diffusive. And maybe there is many factors, but one problem is the spatial resolution of the simulation. And one problem is also just the initial flux is not enough. But if we include the larger magnetic field, the simulation is more difficult. So currently we only set the flux tube around 30 megameter, such a shallow layer.
Yeah, I think this is an interesting problem because, we've been working on similar things as well. And how a structure survives, deeper convection is a difficult question. Your simulations have zero actual diffusion in them. They only have numerical diffusion, right?
Yeah,
so
yeah.
These things the best chance possible to survive from deeper to 20 megameters, if you started them deeper, as they could possibly have, and yet they're not surviving. So I think that's a very interesting question, which isn't addressed. That wasn't the point of your talk, so I don't want to distract from that. Which your points are very interesting, but. I would really like to know what happens from deeper down.
Okay, well, let's move on to Paul Rajaguru, and then Georges has a question online.
Hi.
Hi.
Thanks. Very interesting talk. I have a question on your depth profile of the horizontal divergence. Probably slide number 22, I think.
Number 22. This one.
Yeah, so the horizontal divergence seems to show up at the supergranular scale only at 10 megameter or so not at the surface itself. So this seems to be a very interesting difference between what we see on the sun and probably here. On the sun, we see a very nice horizontal divergence at the surface, which reproduces a supergranular. Which is there something which is
sorry,
learn from here?
I didn't know that. So thank you very much for good comment. So yeah, actually, I don't know why we can't find the horizontal divergence in shallow layer. So yeah, we will have to consider about that. Yeah.
I have one more question, Amy. I'm just trying to understand what's the role of the initial helicity you put in the flux tube. So you said that some of that is converted into Wright.
Yeah.
So what is, the convection itself doesn't twist the field. Is that what you're concluding?
Yeah, I think we think the positive helicity was already installed from the initial state. So, sorry. So this initial positive flux, it is just given from the initial state. Positive helicity is converted to the positive Wrights, and the positive Wrights means anti-clockwise rotation of the sunspot. So
the convection itself doesn't contribute to twisting the field.
Yeah.
And how much helicity is on the flux tube? Initially.
Sorry, I don't remember the number.
Okay.
Yeah, I don't remember the number, but
well, we can get it in the paper, maybe.
Yeah. It's very strong. We use the force-free twisted flux solution. So twist is very large. Yeah.
All right. Okay. Thank you.
Okay, and then Georges, did you want to ask your question?
Sure, yeah. Takafumi-san, very nice talk. Thank you so much. So I had a question. This setup obviously used one flux tube, as you very well showed in your talk. I wonder how different you expect your conclusions to be. So you have several bullet points here in the case that you had more than one flux tube emerging.
That is also our next. We thought it was the next step of our simulation. So if we include multiple flux flow, what happened? And we started, but the stereo reality is not converged. So yeah, actually we are trying to include multiple flux flow, and then maybe Toriumi-san or Hotta-san will analyze the result. So
I see. Hopefully in the larger box to address Nick Brammel's comment as well, which I think there is something to it as well. Yeah. Thank you so very much. Appreciate it.
Thank you.
Are there any other questions? I would like to just say a few things. I think you and I talked about this at TESS, but if these flows are sampling the flux at depth and then bringing the flux to the surface in the way that you described, I wouldn't expect the distribution of the delta spots to have as much anti-hail tilt as we do see in the sun. So that's just an observational aspect that I would wonder how it could be addressed, or how you could get anti-hail spots out of this. I mean, and maybe if the helicity is, if the twist is converting to rise, that's one way, but I mean, that's a different scenario than the supergranule accumulating flux, like the way you were discussing.
So basically our simulation did not include a Coriolis force. So basically, maybe it is a competition between the Coriolis force and the rise, converting the rise. And so the converting to the strength of rise also depends on the initial twist or such kind of things. So yeah, if we perform more parameter survey, maybe including Coriolis force, maybe it will be solved. Yeah.
And then one other aspect, I can't quite connect the picture that was shown in the very beginning that looked like a U-loop to the other picture that showed the supergranular upflows and converging flows having, accumulated flux being pushed together. I'm not sure if, my point is this: if it's a U loop emerging and not an omega loop emerging, you would expect to see less horizontal flux in between the polarities as they emerge. And from, less horizontal flux is sampled by the vector magnetogram. And to my knowledge, there's been, it just seems like there's a lot less flux emergence that lacks the horizontal field in between the bipoles. I mean, there are reports in the literature of U-loops, like I think Lydia Van Gile and others, but it's just a question, like if they are U-loops, then, and not omega loops emerging, then you could differentiate that with the sampling of how much horizontal field is between the bipoles.
Yeah, actually, we haven't analyzed the detailed structure of magnetic field because there's many cases.
Right.
So, yeah, so, but I think maybe both happened depending on the cases. So
that would be interesting to see what the horizontal field looked like in your cases between the bipoles.
Yeah. So I think horizontal field, so in the previous paper of Hotta, Toriumi and Hotta, basically there is a strong horizontal field in some paper.
Okay.
So, yeah, but I didn't check all of the cases in our present simulation. So yeah.
Okay. Well, are there any other questions? I can't see. Oh, Bill has his hand raised.
Yeah, I just have a quick question. So some of the comments involved asking, well, what would happen if you made your box significantly bigger? So I guess my question is how limited are you right now? I mean, how much headroom do you have? So example, if we were to say, hey, could you make your box 3 times bigger? I mean, you're obviously limited probably by the resolution at the surface to get the surface layers, right? So I'm just curious, how much bigger do you think you can make this type of simulation?
Okay, so basically current resolution is maybe almost upper limit. So if we extend the simulation box 3 times, we need 3 times of the numerical resources. And we will have more simulation data. Currently, we have 60 terabyte for offset. So we will have 180 terabyte for all the simulation set. So,
right.
So basically the speed of simulation is very good. So we can accomplish all of the simulation within a week, even if we extend the simulation box to 3 times, if we can use Fugak supercomputer. But maybe if we got larger data and there is a problem to where can we save the data, or also there is another problem that how can we analyze the data. So that is a practical issue for this study.
Okay.
Yeah.
Okay, I don't see any other raised hands, so we can conclude now. And thank you so much for agreeing to give the seminar. It's really
Thank you very much.
well-posed questions and results for the COFFIES Flux Transport and Emergence group. And I think we all enjoyed it. So thank you so much.
Thank you.
Well, thank you again. Some claps. Okay. Bye-bye. Thanks for joining, everyone.
Thank you.
And see some of you on
Bye.
Friday.
Thank you, everyone.
Thank you.